Hey y'all, today we're going to talk about how we can once and for all determine if a reaction will be spontaneous or not. And so here we have a problem. Is the reaction between hydrogen gas and oxygen gas in their standard state spontaneous at 298 Kelvin? Now, again, in their standard state, remember when we talk about something being in the standard state, we say, okay, we're dealing with a pure solid or a pure liquid. If we have a gas, the partial pressure of any gas in that particular thing is 1 atm, and if we have any solution, then the concentration is 1 molar. And so we'll get into that a little bit more. But so when we talk about things in their standard state, right, what you'll start to see is this little naught sign here. So we have delta G naught or delta H naught or delta S naught, that little 0 degree sign at the end. All right, you see that that's telling us that the reaction is occurring when the substances are in their standard state. So basically we have a reaction here where we have the formation of water from its elements, and we just want to know, hey, is this reaction spontaneous, right? So as we talked about yesterday, we need to know what delta G is in order to do that. So there are a couple different ways that we can do this. Number one, since the reaction is at 298, right, we're able to go to the back of the book. And when we go to the back of the book, again, remember we see these things. We see delta H, we see delta G, and we see what should be S. I don't like the delta sign. I think that's a misprint. So we see that in the back of the book, they have delta G data. We're like, sweet, right? Makes life easy for us. Now, the great thing about the back of the book is it makes life easy for us. The bad thing about the back of the book is it's only relevant if the reaction is taking place at 298. We can't use the data in the back of the book for delta G if the reaction is occurring at a different temperature. But since this reaction is occurring at 298, we can kind of see, and if we say, okay, well, we can use delta G. Delta G we find like we would delta H if we're using the back of the book and using formation. So basically we have, well, we're going to have delta G F of the products minus delta G F of the reactants. So again, now we're back to products minus reactants. We're using the delta G of formation, so kind of like we would do for Hess's law. So if we were actually looking this up in the back of the book, right, we would say, okay, well, there's two waters, and the delta G for that as a gas would be 229, right? And then we look and we say, okay, well, then we have two hydrogens. But again, if we look, like we have aluminum and barium, delta G for elements in their standard state is going to be 0. So the delta G of formation for those elements, because again, there's no formation reaction for elements. So we can see that, and then for oxygen gas, it's in its standard state. So we're going to say it's 0 as well. So really here we just see that delta G for this particular process would be equal to a negative 458 kilojoules. And we're like, ooh, negative. So in this particular case, at 298, we would say that this reaction is spontaneous. All right. Now, the other thing that we can do, right, as we introduced yesterday, is we could also say, well, couldn't we use delta G naught equals delta H naught minus delta, or minus T delta S? Okay, because that's the relationship that relates the enthalpy change and the entropy change to what delta G is. And again, for this case, we could use the back of the book and we could figure out, okay, well, delta H, not for this particular reaction, is going to be negative 484 kilojoules. And I could also figure out delta S for this reaction, and delta S for this reaction is going to be actually negative 89 joules, which we would predict, right? We would predict a negative sign for delta S, since we're going from 3 moles of gas to 2 moles of gas, right? So we're going to predict that negative sign there. So then we have this, notice one's in kilojoules and the other one's in joules. So I usually just convert what S is, delta S 0.089 kilojoules. And if we do this and we say, okay, well, delta G is going to be equal to now negative 484, right, minus T, and again, in this case, T is 298 times 0.089, and we do that calculation, and we see that delta G, in this case, is going to be equal to negative 457.5 kilojoules, which is the same thing that we got here, right? So we got the same thing going on there. That's what we would expect to get, right? And so, boom. And you're like, well, why would I do all these different steps, right? If I can just do that, it's really easy, one step. We don't have to worry about finding delta H and delta S, right? Well, the problem is, well, what happens if this reaction is not there, but it's here, right? And it happens at 600 Kelvin. And we want to know, well, is this reaction at spontaneous at 600? Yeah, go away. Right? And so, and again, we look at that, and here's the thing, right? We look and we say, oh, well, delta H is negative and delta S is negative. And when the two things are negative, as we learned, right, is that this could or could not be spontaneous, and it depends on the temp. And this thing tends to be spontaneous at lower temps. Now again, low, high is all relative. We just know that as we increase the temperature, it's going to become less spontaneous. So let's say we increase the temperature to 600 Kelvin. Will the reaction still be spontaneous? And so now, in that particular case, we cannot do this, right? We're no longer at 298. That formula right here no longer applies to us. We can't do this. We have to use delta H and delta S in this formula here when we're at a different temperature other than 298. And so in this case here, we would say, well, delta G delta G naught is going to be equal to delta H naught minus T delta S. And again, we would expect the products become more, or the entropy to go up as the temperature increases, as we've talked about. And so we say, well, delta G is going to be equal to, now we know delta H is not affected by temperature change because it's all about breaking bonds and forming bonds, but entropy is not. And so this would be our 600, right? And now we have times that 0.089. And so in this case, we would have 600 times 0.089. And so, yeah, 600 times 0.0. Yeah, that's right. So that's going to be negative 484 minus 53.4. That's actually a positive sign. And so we can see here 484 plus 5. Oh my gosh, sorry guys, 484 plus, and that drops that to negative 430.6. Okay, and so you can see that the closer the delta G gets to 0, right, if it's a negative value, the closer it gets the less spontaneous it's becoming. So we'd expect as we increase the temperature, in this case, since H and S are negative, that it's going to become less spontaneous as we go along. So then the question becomes, well, at what temperature will we actually see the spontaneity change? Right? We're like, oh, well, I don't know. Well, in this case, again, we're going to sit there and we're going to attack this by saying we have delta G equals delta H, and again, our not signs minus T delta S, right? But this time we want to know what that temperature is, all right? We're looking for that. And so how do we know it? Well, we know it changes spontaneity when it goes from being a positive to a negative. And so one thing that we can do is say, okay, well, when does that change happen? Well, we know that change happens after it goes through equilibrium, in which delta G equals 0. So if delta G equals 0, then we can say, okay, well, then we have our negative 484. Then this is going to be minus T, which we're looking for, and now this is 0.089. And so we're going to get a positive 484 equaling negative T 0.89. I'm sorry, that should be a positive sign because that's negative. There you go. That makes more sense. Sorry, guys. So now T is actually going to be equal to 484 divided by 0.089, and we're going to see that this thing is going to be here becomes non-spontaneous at temps greater than that 5483 Kelvin. All right, and so this is when we would see it going from to equilibrium, and we would see the shift from a negative delta G to a positive delta G at that particular temperature. Okay, and so I want to correct this because I was getting a little bit crazy. So that's what it should actually look like. And so if we do that, then we're going to get that positive sign there because those two things will give us a positive. All right, so hopefully that made sense. And let me know if you have any questions about how we can use delta G. You're going to have some practice problems to work. And so I hope you have a great weekend, and we'll see you again on Monday. Peace, love, happiness. Thanks for playing.